SwayamPrabha. Digital India. Educated India.
Okay, this is another experiment in which we shall study the vibratory system. The system that we have now is a sonar transducer. This kind of a transducer is there on the torpedo nose cone. There are many of them like this. So, the sensor here is one of them, and the job of this sensor is not only to act like a sensing element for for detecting the signals coming back after the sonar signal is reflected from an object, but also is to generate the signal. So, this transducer is fed with a signal, and the signal basically is fed at a frequency which is the natural frequency of the transducer. So, when you feed the signal which is the same as the natural frequency of this transducer, then the output vibration from the face or the front the head of this sensor, the amplitude is large enough, and then you have a strong signal which is radiated out. The reflected wave is also sensed using this particular sensor. So, the objective in today's experiment is to find out the frequency of this sensor, the natural frequency of this sensor, by detecting the resonant condition, right. So, what we are going to do is for finding out the natural frequency of this entire sensor unit, we are going to feed it with a signal whose frequency we are going to scan over a large frequency band and check where the amplitudes of vibration increase. Now, we are going to put a sensor at the top face of this transducer, and we will keep on recording or tracking the vibration amplitude as the frequency is swept across a reasonable frequency range. Now, the sensor itself is a vibratory system. So, what you notice here is there a metallic block here at this point. There is a front face which we call as a head, and between these head and the mass you would observe 6 piezo discs which are mounted, and the discs are separated. Each piezo disc is separated by an electrode, and the electrode has an epoxy layer on either side separating it from each of the piezo disc. So, there are 6 of these piezo discs, and each disc is separated by an electrode, and these are all connected. These electrodes are connected, as you notice here, and what you notice is that the wires connecting the electrodes are taken out, and we are going to feed the signal through these wires. Now, these discs are actually hollow discs. That means they are like the disc is like having its own inner diameter and outer diameter, and through these discs pass this stress bolt. That bolt passes through the threaded hole in this particular tail mass, and the head mass, the bolt is connected to the head mass. This nut, what you notice here, is going to be tightened so that these piezo discs are always in compression, and we learnt it in the single degree of freedom force vibration response that a typical accelerometer is nothing but piezoelectric material compressed using a proof mass, and as the mass vibrates, the piezo discs generate a charge, and that charge output is proportional to the acceleration that it records. Okay. So, these sensors are arranged in an array in the torpedo nose cone, and the job of the sensor is to not only radiate the signal of a desired frequency, but also to detect the incoming waves transmitted through the fluid. Now, the exact configuration of this sensor is what you see here. Each of these piezo discs are like a tubular cylindrical pieces separated by an epoxy put on either side of this red colored electrode, and so what you notice, there are multiple such electrodes which are connected, they are all joined together, and the output is then fed. So the output from this is given to an appropriate electronic equipment to record the signal. Okay. And the head mass has a stress bolt running from this head mass to the tail mass, and then the objective of this central stress bolt is to keep these piezoelectric discs always under compression. So after you screw in the nut, the tail mass and head mass basically compresses all the piezo stack under compression, and that is how this entire system acts like a vibratory system. Okay, so what we have here is we have placed an accelerometer on the head mass, and the accelerometer now records the signal which is generated through the piezo stack here. And to this piezo stack, what we are doing is using a signal generator and the power amplifier, we are feeding the signal as an input signal to the piezo stack. So as the signal of a desired frequency is given, the piezo stack vibrates because of the the fluctuating excitation signal, and the output of this head mass is recorded by a sensor connected at the tip, and the output through a signal conditioner is shown on the oscilloscope here. Now what we are going to do is scan certain frequency range. Now approximate frequency, natural frequency of this entire stack as a vibratory system is known. So I am going to scan through a small frequency range which is going to start with 18 kilohertz, and you can notice the amplitude will increase as I approach the natural frequency of this piezo stack sensor. So I have now shifted from 18 kilohertz to 19, and now when I take it to 20 kilohertz and then 21 and then 22, as you can see, the amplitudes are rising because the vibration of this sensor is closer to the natural frequency, and so we are approaching a resonance condition. So right now it is 22 kilohertz, and suddenly if I shift it from 22 to 23, the amplitude drops, which means that near 22 or 23 hertz I have one resonance which is definitely appearing here. If I increase it further, there is an increase in the amplitude of vibration. So currently the frequency is 24 kilohertz. Now if I move it further, you can see a sudden increase in the amplitude when the frequency goes to 25 kilohertz. So it's quite clear that if it goes down again when I increase it from 25 onwards, so sudden drop means that the natural frequency could be lying somewhere between 24 to 26 kilohertz. Now what we can actually do is I can shift it not in 1000 hertz, but maybe we are going to increase the frequency in steps of 100 hertz, so that we are able to precisely catch the resonance frequency, and therefore you can see that the frequency now is 24.5, 24.6, 24.7, 24.8, 24.9 and 24. Sorry, this is 25 and okay, so this is 25.1, 25.2, 25.3, it starts dropping. So let me go back. Now it is 25.2, 25.1, 25, and so it is precisely 25.1 hertz. That's the resonance condition that I can see. About 25 kilohertz is the frequency. Okay, now let's catch the second resonance. Now we observed it that the frequency was the first frequency. You can see now I am coming back from 22.5 kilohertz. If I keep reducing the frequency, you can see that the amplitudes are rising and then it drops. So the frequency at which I get a peak vibration is 22.3. So 22.3 and 25.0 are the two natural frequencies that we observe from the resonance condition. Now this is a high frequency vibration. It's difficult to see visually the vibrations of this entire stack, but what we are making use of is the sensor which is placed on the head mass here. The head mass vibrations are recorded using a sensor. Now, here again the sensor mass is going to slightly alter the natural frequency that we are measuring, because the sensor has its own mass that gets added to the mass of the head mass, but a slight error is acceptable in this case. A non-contact type measurement sensor can also be used to record. Okay. So, I will just scan through the remaining frequency range. So, I am now reducing it from 21 to 20. So, at 20 also I do not have any vibration which is increasing around that frequency. So, basically the frequency that we have observed, that 22 and 25 kilohertz, these are the two resonant frequencies of this stack. Now, what we are going to do is to give you all the data related to the dimensional details of this sensor. So, we are going to give you the thickness of all of these piezo stack, the material properties of this. What you have to do is to model this entire system as a probably a 2 degree of freedom vibratory system. What we can do is we can treat this to be one mass, this to be another mass, and all these piezo stacks can be treated like a flexible element. So, the spring representing all the piezo stack can be evaluated based on the material properties and the geometric properties of the stack, and based on that stiffness property you can model this as two masses connected by a spring. Now, that spring also has to account for the bolt which passes through the center, and therefore, this bolt and the piezo stack, obviously you have to decide as to how they are connected. Are they in series or are they in parallel? Similarly, all of these individual piezo discs are placed one above the other. So, whether these individual discs are they to be treated like springs in parallel or springs in series is something which you have to work it out. So, in the handout I am going to give you all the dimensional and material properties. This entire system, the sensor unit, has to be modeled like a multi degree of freedom system, and your analysis should generate a frequency, and the measured frequency we have already discussed that the value of the natural frequency is about 25 kilohertz, and the other one we observed was around 22 kilohertz. So, those frequencies, whether they match with your analytical frequency value, is something which is the task in this particular experiment.